All right, so our presentation is on how we use transformer architectures to detect stances of political tweets. So right now, polling is a very common way to uncover how people feel about candidates or policies and much more, but there are problems with the whole process. For instance, they're expensive to do and they're time consuming. So with this in mind, our group had a different approach in going about this. So right now we're in the 21st century where people post their opinions all over the internet, and namely Twitter, because it's easily accessible and it's anonymous. So this essentially gives us a whole database of opinions on a certain issue, and we can actually use this to figure out dominant stances on things such as macro elections. And in fact, this has actually been done before. The Indonesian presidential election is an example of this. However, it was never done on a local policy-based election, which can be just as important, and that's what our paper focuses on. So for some background of our paper, predicting the turnout of elections is very important because it helps politicians better represent constituents, and it lets them know where to focus their campaigning strategy on and how many resources need to go into certain parts of their campaign. And polling is also very common in predicting elections because it gives concise data about the support of a person or a topic. But there's also misrepresentation when it comes down to it. For example, many people don't know about the topic they're voting about, so the data is ultimately skewed and it's not always accurate. An example of this is the Don't Say Gay bill, which had a very large difference from the polls to the actual results. And this was due to how news stations explained the bill. And like I said before, Twitter is a gold mine for sentiments because the tweets are short and there's a lot of them, meaning more data. And it's actually been successfully used on national elections before. And some common models are recursive neural networks, temporal convolutional networks, and bidirectional models.
So in our work, we've come across some common challenges. The first one would be that neural networks are pretty prone to overfitting because they learn so many different parameters while building the model, allowing it to overfit and achieve lower accuracies. Another challenge is that irrelevant tweets are also included in our datasets. For example, some tweets that aren't relevant to Prop 16 but include the word prop or 16 may be included. And our third challenge was that not all tweets had a stance. News articles, questions, or things like quotes are neutral even though they are relevant and may be hard to detect. We focused on achieving three main goals. The first was to train a relevancy classifier to determine if a tweet is relevant or not. Our second was to have a model to detect stances of tweets on localized policies, such as being for or against a policy. And our third was to be able to apply the model to actual elections, such as the Prop 16 election. To achieve our goals, we developed a solution using two approaches. Our first was a modular approach, which is where we determine three things: relevancy, neutrality, and stance separately using three different models. Our combined approach determined all three together at the same time using just one model.
So for the methodology, we first started by using a Twitter API to gather a data set of tweets relating to Prop 16. Then we performed data annotations for each tweet by hand. From there, we had two approaches. One was a modular approach where we created three models, the first being a relevancy classifier, where we determined whether or not a tweet was related to Prop 16. The second was a neutrality detection, which we determined whether or not it was a comment, so if it had a stance or not. And the third was if it did have a stance, if the stance was supporting Prop 16 or against Prop 16. The second approach was a combined approach where we did all the three: relevancy, neutrality, and stance in one model. In terms of getting the data, we used a Twitter API to gather the data set, and then each author labeled 500 tweets by hand to determine their stances. To ensure that we were all annotating the tweets the same way, we annotated an additional 50 tweets that had already been done by someone else and got a Cohen's kappa score of 0.85, which signifies nearly perfect agreement.
This is our model pipeline. After manual data annotation, we were able to find the ratios of negative tweets to positive tweets, which is important later. After this, we used a byte level BPE tokenizer to get the data into a numeric format for the model. This specific tokenizer allowed us to use a compact way to preserve the data. Finally, we used pre-trained transformer models, BERT, RoBERTa, XLNet, Distilbert, and DeBERTa to train on the data. These had varying accuracies based on the model. For example, BERT was trained on actual tweets as part of its corpus, so it performed a bit better than some of the other models that were trained on different types of data. After this, we trained each of the models on different numbers of epochs to see which ones performed the best on the validation data without overfitting. For our stance detection, after our relevancy was classified, we were able to numerically encode each data, which is basically just assigning a numeric value to each of the possible outcomes. When we trained models based on this numerically encoded data, we found that it didn't perform as well because of something called the dogs and cats paradox, where if you have a lot of training data that represents one demographic, the test data will overfit towards that demographic. To fix this, we were able to augment the data by oversampling comments and positive tweets to match the amount of negative tweets, which greatly improve accuracies. We took two approaches to this model. The first thing we did was create two binary classification models. The first would just determine neutrality, and then based on the results of that, we would be able to determine stance. These models performed well when they were tested on their own, but when they were combined into a pipeline, they did not perform as well. Next, we created a ternary classification model, which predicted neutrality as well as stance at the same time. This model ended up performing better than the binary classification models. Next, we tried in our combined approach, the quaternary stance detection. So the main difference between this and the ternary classification is that this just predicts relevancy as well. This model was trained on the RoBERTa base and fine-tuned on the tweets, and this ended up outperforming all of the other models.
So ultimately, after we trained several models with different bases, we ultimately discovered that BERT, which is a specific model, slightly outperformed some of the other models for the relevancy classifier specifically. So when compared to the original hand annotated dataset, it had an accuracy of 98.2% in comparison and an F1 score, which measures the performance of the model, to approximately 0.99, meaning it had a very high performance and accuracy. And this is possibly due to BERT's training based on Twitter data and also because of its use of mass language modeling. Mass language modeling blocks out several words in a text to look at the context of the sentence overall. Because context is very important in determining relevancy, this means that BERT would have a higher accuracy when it comes to determining the relevance of a sentence. And also, our models averaged approximately 10 epochs for maximum performance, meaning that it cycled through the data at least 10 times before obtaining these high results that you can see in this data set. Next, we have our stance detection models, which included a ternary model and two binary models stacked together. And specifically, the ternary models ended up outperforming the binary models. Both of them used RoBERTa, another similar model to BERT, which had an accuracy of 0.84 when it came to the ternary model and a final accuracy of 0.78 when it came to the two binary models stacked together. These accuracy metrics are a bit lower compared to the relevancy classifier, but that makes sense because it is put through many different stances, and it also requires a large number of randomized data sets. So which means that ultimately the accuracy and performance were a bit lower than usual. And RoBERTa may have outperformed some of the other models because it has an optimum optimizations enabled to train large batches of data, meaning that the large number of data sets, which included 3,000 tweets, be more optimum to go through RoBERTa than some of the other bases. And this time, instead of 10, we had anywhere between 5 to 12 epochs for maximum performance. Finally, we have our quaternary model, which had 4 different results, and this outperformed the modular approach and specifically the combined stacked model. So it had an accuracy of 0.78 for the ternary model, but with the quaternary model, it had an accuracy of 82.12%, meaning that it outperformed the stacked models. And this time it was trained with Roberta model again, and it also had 20 epochs, meaning it had to cycle through the data set multiple more times in order to gain a higher accuracy. Ultimately, we were able to predict the failure of Prop 16 with 66% of a split against Prop 16 and a 34% split in favor of Prop 16. Meanwhile, the actual split in the election was 57% against Prop 16 and 43% in favor of Prop 16, meaning that we were able to obtain a similar accuracy in terms of the stance towards the actual election.
In conclusion, we were able to accurately predict the outcome of Prop 16, wherein the two types of models had an 82% accuracy in predicting sentiments overall. Our determination from the models that Prop 16 would have failed was correct, as the proposition did not pass with roughly 7.2 million votes for yes and 9.7 million votes for no, which meant that 57% of voters in reality went against Prop 16, as stated by Aditya. This margin is similar to our model predictions, which stated that 66% of voters would go against Prop 16. This presents our model as an adequate alternative to traditional polling, which has proven to be costly and often inaccurate and ineffective. Our accuracy scores prove that our models are effective in determining local election results. Could you go to the next slide? Now to discuss future applications and potential for further research. We noticed that there is a bias in social media, especially in Twitter, because it is mostly privileged groups that use Twitter. And so they're likely to be overrepresented in the Twitter data sets that we use for our models. We could thus train models on other elections in an attempt to detect and account for such biases in the future. We could also apply our models to current political issues in order to gather voter sentiment through social media policies, through social media without traditional polling methods, and use the results to predict the outcome of controversial policies and to compare if it's a suitable replacement for traditional polling. Prop 16 could also potentially be voted on again in California's 2022 elections. Thus, our model could prove useful there.
So we would like to acknowledge our mentor, Michael Lutz, the Twitter API, which we gathered our data from, and our other mentors, Saurav Kumar, Arjun, Rajaram, and Connor Laden.
These are the references we used for our presentation, and we thank you all for listening to us today. The floor is open for questions. Thank you.
Perfect. Thank you so much for that presentation. Wow, that was really fascinating to see that this model predicted better than a lot of polls. Some of the polls, keep in mind, were saying that Prop 16 was going to pass. And so it's really interesting to see how just using Twitter was able to predict the election pretty accurately. So really great stuff. Do we have any questions currently for these group of students?